Hello, and welcome to the Science Pulse. Tonight, we will talk about the most haunting secrets of space-time. In the vast silence of the cosmos, there exists something more elusive than the stars themselves. It is not made of light or dust, nor of gas or fire. It cannot be touched, yet it touches everything. It bends the paths of planets, carries the weight of galaxies, and holds the memory of every moment since the beginning. This unseen stage is space-time, the quiet fabric upon which existence unfolds. To imagine space-time is to confront the invisible threads that bind reality. Stretching and curving, it is a fabric that listens to mass and energy, shaping the dance of worlds with an elegance that seems almost deliberate. Yet hidden within this fabric are fractures and shadows, places where its logic collapses into silence, black holes where time itself is devoured, horizons beyond which light may never return. And the mystery does not end there, for space-time is restless. It expands faster and faster, carrying galaxies away into darkness. It ripples when stars collide, trembling like a drum struck by celestial violence. It may even boil at the smallest scales, flickering with quantum uncertainty, hinting that beneath its surface lies an ocean of chaos we cannot yet see. But the most haunting secret is not what space-time shows us, but what it conceals. For if space-time is not fundamental, if it is only an illusion, a shadow cast by something deeper, then all of reality as we know it is a fragile mask, stretched thin over a mystery far greater than we dare to imagine. The discovery of the invisible fabric. In the early years of the 20th century, reality itself began to fracture. For centuries, time had been imagined as steady and universal, ticking away like the metronome of the cosmos. Space was thought to be the silent emptiness in which matter floated, an arena rather than a player. These ideas felt unshakable, as natural as the rising of the sun. Yet even as the 19th century closed, cracks had begun to show in this comfortable vision of the world. It was Albert Einstein who shattered it completely. In 1905, working alone in a modest apartment in barren Switzerland, Einstein looked at the world with a question few dared to ask. What if time itself could not be trusted? What if the speed of light, not the rhythm of clocks, was the true constant of nature? From that thought was born the special theory of relativity, a theory that declared space and time inseparable. Events that seemed simultaneous in one frame of reference would not be simultaneous in another. The old absolutes dissolved, and in their place, a strange new fabric emerged: space-time. This was not a fabric one could see or touch, yet it governed every interaction in the cosmos. To Einstein, space-time was not a backdrop, but a structure, woven from the threads of geometry and energy, where distance and duration were not fixed, but pliable. Acts showed that motion itself bent perception, that clocks could run slow and rulers could shrink, not by illusion, but by the fundamental structure of reality. The world was stunned. At first, the theory seemed abstract, a mathematical curiosity. But in 1915, Einstein unveiled the general theory of relativity, an even deeper vision. Gravity, the most ancient of forces, was not a mysterious attraction between masses, but the curving of space-time itself. A planet did not fall toward the sun because of an invisible pull. It moved because the sun bent the fabric of space-time around it, guiding the planet's orbit like a marble rolling in a warped sheet. Here was a revelation: the invisible architecture of reality, hidden for all of human history, suddenly revealed in equations and thought experiments. But science requires more than beauty. Proof was needed. That proof arrived in 1919 when the British astronomer Arthur Eddington sailed to the island of Principe to witness a solar eclipse. If Einstein was right, the sun's immense gravity would bend starlight passing near it, shifting the star's positions ever so slightly in the sky. As the eclipse darkened the heavens, the stars near the sun appeared displaced, exactly as Einstein had predicted. Newspapers around the world declared a new era. "Revolution in Science," one headline read. "Newtonian ideas overthrown." For the first time, the world glimpsed the haunting truth. Space-time was not a silent stage. It was an active participant in the universe, shaping and being shaped, bending and rippling under the weight of matter and energy. This discovery did not merely change physics. It rewrote humanity's understanding of existence. Time was no longer universal. Space was no longer flat and infinite. The cosmos itself was alive with structure, more fluid and mysterious than anyone had dared imagine. Yet with this revelation came unease. If space-time could bend, what else could it do? If it could curve, could it also tear? Could it collapse upon itself, or give birth to phenomena no human had ever conceived? The discovery of the invisible fabric was not a final answer, but a doorway. And through it, humanity stepped into a universe far stranger than the one it thought it knew. The years following Einstein's revelation were filled with astonishment and resistance in equal measure. Many scientists struggled to accept a reality where time slowed near fast-moving objects, or where rulers could shrink depending on perspective. These ideas defied common sense, and yet experiment after experiment began to confirm them. Physicists devised precise measurements using atomic clocks. Jets carrying these clocks across the globe returned with their time running behind those left on Earth. Particles in accelerators lived longer than they should. Their internal clocks slowed by near-light speeds. Even the faint muons raining down from cosmic rays survived long enough to reach Earth's surface, only because of relativity's dilation of time. The invisible fabric had spoken, and its whispers were undeniable. It was not just the scientific community that felt the weight of this change. Philosophers, poets, and theologians began to wrestle with the implications. If time itself was relative, then the very foundation of human experience, memory, anticipation, the flow of life, was bound to a fabric that was neither absolute nor universal. The haunting idea emerged that reality was not fixed, but pliable, shaped by the conditions of the observer. This revelation also forced humanity to rethink its place in the cosmos. No longer was it adrift in an empty void, but suspended within a living fabric, a continuum where presence and motion altered the shape of existence itself. Yet Einstein's equations hinted at something even more profound and unsettling. In their depths lay the seeds of predictions too strange to believe. Objects so dense they would tear space-time into a funnel from which nothing could escape, and a universe not static but restless, expanding, and perhaps destined for a fate none could escape. The discovery of space-time was not just the unveiling of a hidden fabric. It was the beginning of an era where reality itself would appear fragile, haunted by secrets just beyond the reach of certainty. And it was only the beginning, the first tremors of doubt. For centuries, time had seemed untouchable. It was the measure of change, the silent current flowing beneath every event. Philosophers spoke of it as absolute, the same for gods and men, the same for planets and stars. Isaac Newton had declared it in the 17th century. Time flowed equably, without relation to anything external, a universal heartbeat of the cosmos. But Einstein's revelations struck at the very heart of this certainty. His theory of relativity did not merely suggest that time could bend, it declared that it must. The first tremors of doubt rippled through the scientific world. If time was no longer absolute, then simultaneity, the simple notion that two events could occur at the same moment, dissolved into relativity. A flash of lightning striking two ends of a train might be simultaneous for the observer standing on the platform. Yet, for the passenger rushing inside the train, the flashes would not occur together. Each perspective was correct, yet each was irreconcilable. This was not a trick of perception. It was a reweaving of reality itself. Time had lost its universality, and with it, the comforting stability that had guided human thought for millennia. In the quiet halls of universities, in lecture theaters and research institutes, the debates grew heated. Many resisted. To imagine a world where time was not fixed felt like surrendering to madness. How could the universe function if one person's now was another person's then? Yet evidence began to pile up. Physicists realized that Einstein's ideas explained mysteries that Newtonian physics could not touch. The orbit of Mercury, long a problem for astronomers, deviated slightly from Newton's predictions. Einstein's curved spacetime accounted for this perfectly. Light itself, once imagined as untouchable, was shown to bend under the weight of gravity. Each confirmation deepened the unease. For if space and time were part of the same fabric, then they were not immutable. They could stretch, curve, ripple. They could fail. To ordinary people, these ideas felt like a kind of sorcery. Time dilation, the slowing of time under motion or gravity, became one of relativity's strangest consequences. Imagine a pair of twins. One remains on Earth, the other journeys at near light speed to a distant star. When they meet again, one twin has aged decades, the other only a few years. It was more than a thought experiment. The universe itself performed the experiment countless times. Muons, unstable particles born in the upper atmosphere, should decay long before reaching Earth's surface. Yet because they race near the speed of light, time slows for them, and they endure long enough to touch the ground. The invisible fabric stretched their lives, granting them moments they should never have possessed. Time, once thought absolute, had revealed its fragility. Philosophers recoiled. If time was relative, then what was the present? Was there truly a universal now, or were past and future bound together in a block universe, where all moments coexist like frames in a film reel? The comforting flow of time, carrying human lives from birth to death, began to look less like a river and more like an illusion cast by consciousness. In this view, every moment, from the ignition of the first stars to the last fading embers of the universe, already exists, written into spacetime. The past is not gone, the future not unborn, but all are stitched together in a cosmic tapestry beyond human perception. For some, this was liberation. For others, it was terror. The tremors of doubt grew stronger with the predictions of black holes. Here was a place where space-time itself collapsed into absurdity. Gravity so immense that even light could not escape. Time, as measured from outside, slowing to a crawl at the event horizon. To cross that threshold was to fall into silence, a region where the laws of physics themselves dissolved. Einstein himself doubted their physical existence. He considered them strange artifacts of mathematics, unlikely to manifest in reality. Yet the equations were relentless, and observations would, in time, prove them real. Even the stars were whispering of relativity's power. Pulsars, quasars, and the bending of light across galaxies revealed a universe haunted by the pliability of spacetime. Each discovery was a tremor, shaking the foundations of certainty. But perhaps the deepest shock was psychological. For if time and space were not fixed, then reality was no longer a solid stage upon which the human drama unfolded. It was a fabric that shifted underfoot, responding to mass, energy, and motion. Humanity was not standing on solid ground at all, but on a living, restless medium that could warp at any moment. The first tremors of doubt, born from Einstein's equations, did not fade with time. They deepened, resonating through the 20th century and into the 21st. Satellites orbiting Earth today, guiding global navigation systems, must correct for relativistic effects every moment, or else their calculations would drift into error. The very technologies of modern civilization now depend upon acknowledging that time itself cannot be trusted. In the stillness of night, when astronomers turn their telescopes skyward, they are not just looking into distance, but into time, into the ancient light of galaxies billions of years old. That light, stretched by the expansion of spacetime, arrives redder, fainter, and slower than when it was born. Even the stars remind humanity that the fabric of reality is mutable, and so the tremors of doubt have become permanent. Humanity inhabits a cosmos where now is not universal, where distance and duration are fluid, where the bedrock of reality shifts under the weight of gravity and velocity. It is a haunting truth. The very framework of existence is unstable, pliable, and strange. And if space-time itself could bend and change, then the question loomed larger than ever. What deeper secrets might this invisible fabric conceal? Strange predictions, stranger confirmations. From the moment Einstein's equations were set loose upon the world, they began to whisper of things almost too strange to believe. The mathematics of general relativity was not content with describing the ordinary dance of planets or the bending of light. It reached into the uncharted, predicting phenomena that seemed to defy common sense, even to the man who had discovered them. Among the strangest predictions was the black hole, a region of space-time so warped that escape became impossible. In Newton's era, some philosophers had mused about dark stars whose gravity might trap light, but these ideas were curiosities, not physics. Einstein's theory gave them form. His equations suggested that if enough mass were squeezed into a small enough volume, space-time would curve infinitely, collapsing into a singularity. Yet Einstein himself resisted this conclusion. He doubted that nature would permit such monstrosities to exist. To him, black holes were mathematical curiosities, artifacts of the equations rather than features of the cosmos. But the universe had already written them into its story. The first clues arrived not from theory, but from the skies. In the 1960s, astronomers began detecting strange flickers of light, powerful bursts of X-rays from distant regions of space. These sources were too compact, too energetic to be ordinary stars. One of them, Cygnus X-1, became infamous. Observations revealed a massive, invisible object pulling matter from a nearby star. The matter spiraled inward, heated by friction, and erupted in X-rays before vanishing into darkness. The only explanation, a black hole, a cosmic pit from which not even light could escape. Einstein's reluctant prediction had taken physical form. The confirmations continued. Pulsars, rapidly spinning neutron stars, pulsed with clock-like precision, revealing the extreme warping of space-time near collapsed stars. Quasars, blazing with the energy of entire galaxies, were soon understood as black holes devouring matter at their centers. The universe, it seemed, was littered with these monsters. Even more astonishing was the discovery that nearly every galaxy harbors a supermassive black hole at its core, millions or even billions of times the mass of the Sun. These behemoths, far from being rare anomalies, are fundamental to cosmic structure. Galaxies themselves may be shaped and stabilized by the gravity of these central titans. The invisible fabric of space-time had grown teeth, and it was devouring stars whole. But Einstein's equations had predicted more than black holes. They had also foretold the slowing of time itself near massive objects. This time, dilation was no longer a philosophical abstraction, but a measurable reality. The Hafele-Keating experiment in 1971 carried atomic clocks aboard commercial airliners, flying eastward and westward around the globe. When compared to clocks left on Earth, the airborne clocks disagreed. Time had passed differently depending on speed and direction. The difference was small, measured in billionths of a second, but it was real. Even satellites orbiting Earth feel this effect. Without relativistic corrections, GPS systems would drift by kilometers each day. The modern world, unknowingly, lives inside Einstein's spacetime and depends on its strange predictions just to navigate city streets. The ultimate confirmation, however, came a century after Einstein's equations were written. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected a faint tremor in reality itself. Two black holes, more than 1 billion light-years away, had spiraled together and merged. The collision released more energy than all the stars in the observable universe combined, but not as light. It rippled space-time, sending waves across the cosmos like the surface of a pond struck by a stone. Those waves arrived on Earth as distortions smaller than a fraction of a proton, stretching and compressing the arms of LIGO's detectors. The signal was faint, but unmistakable. The first detection of gravitational waves, another prediction of Einstein's theory, confirmed. It was as if the universe itself had spoken in sound, carrying the memory of cataclysm through the trembling of space-time. Yet these confirmations, as astonishing as they were, only deepened the mystery. For each prediction proven true revealed layers of reality more haunting than the last. Black holes did not merely bend light, they challenged the very idea of information. If nothing escaped, then what became of the information about the matter that fell in? Did the universe forget? Stephen Hawking proposed that black holes evaporate through radiation, but this only sharpened the paradox. If they vanish, what happens to the data? The laws of quantum physics demand that information cannot be destroyed, yet relativity seemed to allow it. Here, two pillars of modern science collided: general relativity and quantum mechanics. Both were confirmed by endless experiments, both indispensable, yet when brought together, they tore at each other's foundations. The fabric of space-time trembled under the weight of contradiction. And then there were the strange predictions of wormholes. In Einstein's mathematics, certain solutions describe tunnels through space-time, linking distant regions like bridges. These Einstein-Rosen bridges fascinated physicists and storytellers alike. Could they be stable? Could they permit travel faster than light, or even backward in time? Most physicists believe they would collapse instantly, too unstable to traverse. But the equations leave room for speculation. Exotic forms of matter with negative energy density might hold them open. If so, the universe may contain shortcuts, hidden passages carved into its own fabric. The predictions of relativity are haunting because they refuse to remain confined to chalkboards and equations. They spill into the night sky, into laboratories, into technology. They reshape not only the way humans think, but the way they live. Each confirmation has carried a dual weight, triumph and terror. Black holes, once unthinkable, are now photographed, their shadows imaged by the Event Horizon Telescope. Gravitational waves, once whispers in equations, now recorded as cosmic symphonies. Time dilation, once counterintuitive, now a tool that guides billions of travelers daily. The strange predictions of spacetime have become the strange confirmations of human history. And with each revelation, one truth grows harder to ignore. If Einstein's fabric of spacetime can predict monsters, ripples, and paradoxes with such accuracy, what further secrets still lie folded within its equations? Ripples in reality. For centuries, gravity was imagined as invisible threads, pulling objects toward one another across the void. Newton described it as an action at a distance, a force that acted instantaneously across space. It was powerful, predictive, and elegant, but silent. Gravity had no voice, no echo, no vibration. Einstein's vision changed that. In his general theory of relativity, gravity was no longer a mysterious pull. It was the bending of space-time itself, the warping of the invisible fabric under the weight of mass and energy. And if space-time could bend, it could also ripple. The Rao equations foretold this possibility. Accelerating masses, like two stars locked in orbit, should stir space-time itself, sending waves outward at the speed of light. These were gravitational waves, distortions in the very geometry of reality. They would stretch and squeeze space as they passed, though by amounts so tiny they seemed forever beyond detection. For decades, physicists debated their existence. Could spacetime truly ripple, or was it only a mathematical artifact? The waves, if real, would be unimaginably faint. A passing gravitational wave would change the distance between the Earth and the Sun by less than the width of a human hair. Detecting them felt impossible, yet some dared to try. In the 1960s, Joseph Weber built the first crude detectors, massive aluminum cylinders designed to vibrate in response to passing waves. His claims of detection were controversial, never confirmed by others. Still, his vision ignited a movement. Across the world, scientists began to dream of listening to the universe through space-time itself. The challenge was monumental. Unlike light, gravitational waves could not be blocked by dust or absorbed by matter. They traveled unhindered across billions of light years, carrying with them the memory of cataclysmic events. But their faintness required instruments of exquisite sensitivity, machines that could measure changes smaller than the width of a proton. The idea was audacious, almost absurd, but physicists persisted. At last, after decades of design and construction, two vast observatories were built in the United States. The Laser Interferometer Gravitational Wave Observatory, or LIGO. Each consisted of two enormous arms, 4 kilometers long, arranged in an L shape. Within them, lasers bounced between mirrors, measuring distances with impossible precision. If a gravitational wave passed, it would stretch one arm while squeezing the other, altering the interference pattern of the laser light. On September 14, 2015, the impossible happened. The mirrors of LIGO trembled with a signal unlike any seen before. For just a fraction of a second, space-time itself had quivered, two black holes, each about 30 times the mass of the Sun, had spiraled together and merged over 1 billion years ago. Their collision released a torrent of energy, not as light, but as gravitational waves. After crossing the cosmos, those ripples had finally washed across the Earth, nudging the detectors ever so slightly. The signal was faint, yet clear. Humanity had heard the universe in a new way. The discovery was hailed as historic. A century after Einstein predicted gravitational waves, they had been confirmed. The Nobel Prize followed soon after. But more than recognition, this was the birth of a new kind of astronomy. For the first time, humans could observe the cosmos not only through light, but through the trembling of space-time itself. It was as though a deaf species had suddenly learned to hear. The symphony of the universe soon revealed itself. In 2017, LIGO, joined by its European counterpart Virgo, detected the merger of two neutron stars. Unlike black holes, neutron stars are made of matter, and when they collided, they produced not only gravitational waves, but light, gamma rays, X-rays, and visible afterglows. For the first time, scientists witnessed an event both through light and gravity. The cosmos had spoken in harmony, and humanity had listened with two senses instead of one. This event also solved a profound mystery: the origin of heavy elements. The collision of neutron stars forged gold, platinum, and other precious metals, scattering them into the cosmos. The jewelry on human hands, the circuitry in computers, the instruments of science, all could trace their ancestry to the ripples of space-time created in such cataclysms. Yet the story of gravitational waves was more than discovery. It was revelation. These ripples confirmed that space-time is not rigid, but alive, trembling like a drum under the strikes of cosmic events. Each wave carried with it a history, the mass of the colliding objects, their distance, their dance before the final plunge. By decoding the waves, scientists could reconstruct events that happened long before life arose on Earth. The implications were staggering. Black holes, once invisible except through indirect evidence, could now be studied directly. Entire populations of them, scattered across billions of light years, revealed themselves through their gravitational symphonies. Already, dozens of mergers have been detected, mapping a hidden universe of collisions. And the journey has only begun. Planned observatories like LISA, the Laser Interferometer Space Antenna, will place detectors in orbit around the Sun, with arms millions of kilometers long. LISA will hear deeper, catching the whispers of supermassive black holes colliding at the hearts of galaxies. Other projects will search for the faint roar of the early universe, gravitational waves born less than a second after the Big Bang, carrying the memory of creation itself. Philosophically, the discovery of ripples in reality carries haunting weight. If space-time can ripple, then reality is not static. It is not the silent void once imagined. It is a living ocean, restless and dynamic, its waves carrying echoes of birth and destruction across eternity. The universe itself is not only seen, but felt, trembling with memory. And this raises deeper questions. If space-time can vibrate, can it also resonate? Could the universe itself possess frequencies, hidden symmetries that have yet to be discovered? Might there be a fundamental music of reality, a cosmic harmony waiting to be heard? Speculation grows. Some physicists wonder whether gravitational waves could someday be used for communication across the stars, unimpeded by dust or matter. Others imagine they might reveal exotic objects, cosmic strings, hypothetical relics from the early universe, stretching across spacetime like cracks in crystal. What is certain is that the ripples in reality are not only confirmations of Einstein's genius, but also invitations, beckoning humanity deeper into the haunting secrets of spacetime. When LIGO first captured the song of merging black holes, the sound was translated into audible frequencies. A brief chirp, rising in pitch, marked the final moments of the dance. Scientists played it to the world, the sound of spacetime itself quivering from a billion years away. It was simple, almost anticlimactic, yet profoundly moving. For the first time, humans had heard the cosmos not through light, but through the trembling of existence. It was as though reality itself had whispered, "I am not silent. I am alive, the cosmic web." At first glance, the universe appears scattered at random. Stars glimmer across the night, galaxies wheel in distant clusters, and to the human eye, their arrangement seems without pattern. But when astronomers began to map the cosmos on its grandest scales, a hidden order emerged, an architecture vast and haunting, unlike anything imagined before. It was not chaos, but structure. The galaxies were not sprinkled like grains of salt, but strung along invisible filaments, woven into colossal threads stretching across billions of light years. Between them yawned immense voids, cosmic caverns nearly empty of matter. Together, these filaments and voids formed something breathtaking: the cosmic web, the largest structure in existence, and perhaps the most mysterious. The first hints of this architecture appeared in the mid-20th century as astronomers measured the redshifts of galaxies, the stretching of their light by the expansion of spacetime. These measurements allowed positions in 3 dimensions to be plotted, revealing clusters and chains. By the 1980s and 1990s, with surveys like the CFA Redshift Survey, the universe's hidden skeleton began to take shape. Walls of galaxies, tendrils stretching across unimaginable distances, knots where filaments intersected. Later, the Sloan Digital Sky Survey expanded this vision. Millions of galaxies were mapped, their positions revealing an intricate tapestry, as though the universe itself had grown along threads of invisible scaffolding. The scale defies comprehension. Filaments extend hundreds of millions of light years. Superclusters of galaxies link into chains that dwarf imagination. And between them, the voids, vast abysses, tens of millions of light years across, where galaxies are rare and spacetime seems eerily empty. But what creates this web? The answer lies in the unseen. Gravity alone cannot explain such patterns. Ordinary matter, stars, planets, gas, makes up less than 5% of the cosmos. The rest, scientists realized, must be something else, something invisible, yet holding galaxies in place: dark matter. Dark matter does not shine or absorb light. It does not burn in stars or scatter in clouds. It is invisible, detected only by its gravity. Yet simulations of the universe show that without it, the cosmic web could not exist. In computer models, dark matter clumps first, forming filaments and nodes. Ordinary matter then falls into these invisible scaffolds, condensing into galaxies. In this sense, the cosmic web is more than galaxies strung across the sky. It is the shadow of dark matter, a ghostly architecture revealed by light, yet built from the unseen. The scale of the web is staggering. Imagine a single filament, hundreds of millions of light years long, thick as a galaxy cluster, glowing faintly with galaxies like fireflies strung along a thread. At the intersections of filaments lie the most massive structures known, galaxy clusters, each containing thousands of galaxies bound by dark matter halos. These are the cities of the cosmos, bustling hubs connected by intergalactic highways of dark matter. And then there are the voids. They are not truly empty, but compared to the richness of filaments, they are deserts. To fall into a cosmic void would be to drift in near silence, with galaxies scattered so sparsely they would be faint whispers across the darkness. Some voids may stretch nearly 1 billion light-years wide. They are among the loneliest places in existence. The haunting beauty of the cosmic web lies not only in its size, but in its resemblance to the patterns of life. Filaments of galaxies resemble threads of neurons in the brain, or the fine tendrils of mycelium in soil. The largest scales of the universe echo the smallest structures of life, as though existence itself were written in fractals. To study this web is to study the birth and fate of the universe itself. Its patterns were seeded in the earliest moments after the Big Bang, shaped by quantum fluctuations in the primordial plasma. These tiny differences, amplified by gravity and dark matter, grew into the vast scaffolding we see today. The cosmic microwave background, the faint afterglow of the Big Bang, holds the imprint of these seeds. Slight variations in temperature, mere millionths of a degree, correspond to the density fluctuations that would grow into filaments and voids. From the silence of that early radiation, the architecture of the cosmic web was foretold, and its growth continues. As the universe expands, filaments stretch, voids widen, and clusters grow as galaxies fall into them. The web is dynamic, alive with motion, evolving across billions of years. Yet the cosmic web remains one of the greatest frontiers of science. Despite mapping millions of galaxies, astronomers have traced only a fraction of its extent. Much of its matter remains hidden. The diffuse gas-threading filaments, the vast reservoirs of baryons not yet fully accounted for. Some call this the missing matter problem. The faint, warm gas too diffuse to shine brightly, yet crucial to the cosmic balance. New instruments aim to reveal it. Telescopes like the Square Kilometre Array will map hydrogen across the cosmos, tracing filaments in greater detail. The Euclid mission and the Vera Rubin Observatory will map billions of galaxies, expanding humanity's vision of the web to unprecedented scales. The philosophical weight of the cosmic web is profound, for in its filaments and voids, humanity sees both connection and isolation. Every galaxy, including the Milky Way, is but one spark along a thread, part of a structure so vast it defies imagination. Yet between the threads lie voids of silence, gulfs of nothingness where light barely travels. The web suggests a universe both bound together and fractured, both living and haunted by emptiness. Speculation runs deeper still. Could the structure of the web reveal fundamental truths about spacetime itself? Some physicists wonder if the cosmic web is not only shaped by gravity and dark matter, but also by deeper principles: the distribution of energy in quantum fields, or the geometry of spacetime on cosmic scales. Perhaps the web is not just an arrangement of matter, but a shadow of the underlying laws of reality. Others look to the eerie resemblance between the web and the brain. Is it coincidence or a hint of some deeper pattern that the largest structure in the universe mirrors the networks of thought? Could consciousness itself be another echo of the same fractal laws that shape galaxies? The cosmic web is a reminder of both humanity's smallness and its belonging. The Milky Way lies in a filament of the Laniakea supercluster, connected to galaxies millions of light-years away. The stars above are not scattered at random, but are part of a hidden lattice that spans the observable universe. And yet the haunting truth remains. Even this vast web accounts for only part of reality. Dark energy, the mysterious force accelerating the universe's expansion, dwarfs both matter and dark matter combined. The web floats in an ocean of something unseen, something that pushes filaments farther apart, deepening the voids. The cosmic web is not permanent. Over billions of years, dark energy will stretch it thinner, pulling galaxies away from one another. The filaments may dissolve, leaving only isolated islands of stars adrift in expanding darkness. In that far future, the cosmic web may fade from sight, its haunting beauty lost to all but memory. For now, however, the web endures, shimmering faintly in the light of galaxies strung across space-time. It is the skeleton of the cosmos, the architecture of the unseen, the grandest pattern ever discovered. And in its threads and voids, the haunting secrets of space-time whisper still. Time's relentless arrow. Of all the mysteries woven into space-time, none feels more intimate than the passage of time itself. Human lives unfold within it. Birth, memory, decay, and death, all are measured by its silent current. Yet physics whispers that time is not what it seems. Its flow, so steady and familiar, is one of the most haunting illusions in the cosmos. Einstein revealed that time is pliable. It bends with speed, stretches near gravity, and slows in the presence of massive objects. In relativity, time is not a universal river flowing evenly for all, but a landscape, warped, uneven, shifting. To one observer, an hour might pass. To another, racing at near light speed, only minutes. Both are correct. Both are real. Yet beneath relativity lies a deeper puzzle. For the equations that describe space-time work equally well forward or backward. The laws of physics do not prefer the future over the past. And yet, in human experience, time has a direction. Eggs crack, but do not uncrack. Smoke disperses, but does not gather itself again. Life moves forward, never back. This direction is called the arrow of time, and it is one of the most profound enigmas of existence. In the 19th century, physicists sought to understand heat, engines, and the flow of energy. From this study emerged the second law of thermodynamics. Entropy always increases. Entropy is disorder, the measure of how many ways a system can be arranged. A neat deck of cards can be shuffled into chaos, but chaos will not spontaneously align into neat order. Entropy gives time its arrow. It explains why humans remember the past but not the future, why glass shatters but does not reassemble. It anchors the flow of existence in a single direction, forward. But this explanation, elegant as it is, raises deeper questions. Why was the universe's entropy so low at the beginning? The Big Bang should have been chaos, a storm of energy, matter, and radiation. And yet, cosmologists find that the early universe was astonishingly uniform, smooth, and ordered. It is this improbable low entropy state that allows the arrow of time to exist at all. In this sense, time's relentless arrow is not inevitable. It is contingent, dependent on the strange, improbable birth of the cosmos itself. Philosophers wrestle with the implications. If the laws of physics are reversible, then time's arrow is not fundamental but emergent. Perhaps it is an illusion born of perspective, like the motion of a shadow cast by a deeper reality. Some suggest that the block universe view, where past, present, and future all coexist, is more accurate. In this view, time does not flow. Instead, every moment is eternally fixed, stitched into the fabric of space-time. The arrow is simply the path humans trace through it. But if all moments exist equally, what does it mean to live? Are choices real, or are they already written into the tapestry? Is consciousness merely the illusion of movement across frames already in place? The questions linger, haunting and unresolved. The arrow of time is not only philosophical, it shapes the fate of the cosmos. As entropy increases, energy spreads thin, stars burn out, and order gives way to disorder. Cosmologists envision the heat death of the universe, a future where all gradients are erased, where no engine can run, no memory can form, no life can endure. In that distant age, trillions of years ahead, black holes will evaporate into Hawking radiation. Even particles may decay, leaving only a thin soup of photons drifting in endless darkness. In such a universe, time itself may lose meaning. With no change, no memory, no difference between one moment and the next, the arrow would fade into silence. It is a haunting destiny, the universe as a graveyard, timeless and cold. Yet some theories suggest other endings. A cosmic Big Crunch, in which expansion reverses, would collapse the universe back into density. In such a cycle, entropy might reset, spawning a new cosmos with a fresh arrow of time. Others imagine a big bounce, where universes arise endlessly from previous collapses, each birthing new arrows pointing forward from improbable beginnings. Still more radical are ideas from quantum mechanics. Some interpretations suggest that time itself may be emergent, not fundamental, but arising from entanglement, from the relations between quantum states. In this view, time might dissolve if observed deeply enough, replaced by a more primal order without sequence or flow. Experiments have tried to probe the mystery. At the quantum scale, particles do not obey the same irreversible laws as macroscopic objects. An electron can scatter forward or backward in time with equal probability. Only when systems grow larger, entangled with countless degrees of freedom, does the arrow emerge. This has led some physicists to speculate that time's direction is a property of scale. At the deepest level, the universe may be timeless. The arrow may be a macroscopic illusion, born of complexity and entropy. And yet, illusions can be powerful. For human beings, time is not abstract. It is lived, endured, cherished, feared. The arrow of time is the measure of mortality, the shape of memory, the essence of what it means to exist. There is a paradox here, haunting and unresolved. Physics describes a universe in which time may be reversible, where past and future are equal. Yet consciousness knows only a single direction. Between the equations of relativity and the experience of being alive yawns a gulf as deep as any cosmic void. Perhaps, some suggest, the secret lies in the act of observation itself. Quantum mechanics hints that measurement, awareness, entanglement, all may shape the arrow. If so, the human mind is not merely subject to time's relentless arrow, but part of its very creation. The arrow of time binds every story, every life, every memory. It is relentless, unstoppable, indifferent. Stars will die, galaxies will fade, and the universe will drift into silence. Yet within that silence lies a mystery. Why does time flow at all? Why was the universe born with order from which disorder could grow? The questions remain unanswered, but they remind humanity of its place. Creatures of entropy, beings of memory, sparks moving forward through a fabric that may not flow at all. Time's arrow is both prison and gift. It brings endings, but also beginnings. It drives decay, but also allows the unfolding of complexity, the rise of galaxies, the birth of life. Without its relentless push, there would be no evolution, no history, no story to tell. And so, Though physics may whisper that the arrow is illusion, to those who live within it, time remains the most haunting secret of space-time. The expanding universe. In the stillness of night, when astronomers first turn their telescopes skyward, they imagine the universe as infinite and unchanging. Stars drifted in fixed constellations, galaxies thought to be faint clouds within our own Milky Way. The cosmos, it was assumed, had always been as it was, eternal, stable, everlasting. But the universe was not still. It was restless. In the 1920s, American astronomer Edwin Hubble peered into the heavens through the 100-inch Hooker telescope at Mount Wilson, then the most powerful in the world. He measured the light of distant galaxies with extraordinary care, studying the spectral lines that revealed their motion. What he found was shocking. Almost every galaxy was rushing away, their light stretched into red by the expansion of space-time. The farther they were, the faster they fled. The universe was not eternal and static. It was expanding. This revelation overturned centuries of thought. If galaxies were rushing apart today, then in the past they must have been closer together. Extrapolated backward, all matter, all energy, all of space-time itself must once have been compressed into a single, searing beginning. The cosmos had a birth. The theory that emerged was called the Big Bang. At first, many resisted the idea. Einstein himself preferred a static universe, introducing a cosmological constant into his equations to hold it steady. He would later call it his greatest blunder. The Belgian priest and physicist Georges Lemaitre argued for a primeval atom, an initial state of explosive density. Critics dismissed it as philosophy, not science. But Hubble's observations could not be ignored. The universe was alive with motion, expanding in all directions, carrying galaxies apart on the currents of space-time. The evidence grew stronger. In 1965, Arno Penzias and Robert Wilson stumbled upon a faint hiss in their radio antenna. At first they thought it was noise, interference, or even pigeons nesting in the dish. But it was not noise. It was the cosmic microwave background radiation, the afterglow of the Big Bang itself, stretched into microwaves by billions of years of expansion. The universe was filled with this ancient light, a relic of the moment when the cosmos first became transparent. It was proof that the universe had once been hot, dense, and newborn. Proof that it was expanding still. But the expansion was not simple. In the 1980s, theorists proposed that in its first fraction of a second, the universe underwent cosmic inflation, a staggering burst of exponential growth. In less than a heartbeat, space-time expanded faster than the speed of light, stretching tiny quantum fluctuations into the seeds of galaxies. This inflationary epoch explained why the universe looks so uniform across vast distances, yet also why it bears faint imprints of structure. The fingerprints of quantum noise magnified to cosmic scale. The inflationary universe was not only larger than imagined, but stranger. If inflation happened once, it might happen endlessly, spawning countless bubble universes, each with its own space-time and laws of physics. The observable cosmos may be just one bubble in an eternal froth, expanding into a multiverse beyond imagination. Still, even within our own bubble, the expansion carries haunting implications. As galaxies recede, light from them grows fainter and redder. Some retreat so fast they slip beyond the cosmic horizon, their light stretched until it can never reach us. With each passing moment, more galaxies vanish into darkness, not because they cease to exist, but because space-time carries them forever beyond our reach. The night sky, once thought eternal, is slowly erasing itself. Billions of galaxies that shine today will one day be invisible to Earth, lost to the expansion. To distant future astronomers, the universe may appear empty, the evidence of its beginning erased by the very expansion that defined it. The expansion also raises profound questions. What drives it? Gravity, the great attractor, should pull galaxies back together, slowing the expansion over time. And yet in 1998, astronomers studying distant supernovae discovered something astonishing. The expansion was not slowing, but accelerating. Some unknown force, now called dark energy, was pushing space-time apart with ever-growing strength. Dark energy makes up nearly 70% of the cosmos. Yet its nature remains a mystery. It may be a property of space-time itself, the energy of the vacuum. Or it may be something even stranger, a new field, a new force, woven into the fabric of reality. Whatever it is, it ensures that the expansion will continue forever, tearing the cosmos into ever larger fragments. The fate of the universe is written in this acceleration. If it continues unchecked, galaxies will drift apart until only local clusters remain visible. In the far future, even atoms may be torn apart in a catastrophic big rip, space-time itself unraveling into silence. Philosophically, the expanding universe is both terrifying and profound. It tells humanity that the cosmos is not eternal, but evolving. That creation is not a single moment in the past, but a process unfolding still. Each breath, each heartbeat, occurs in a universe larger than it was a moment before. It also challenges the notion of permanence. Nothing is fixed, not even the fabric of reality. Galaxies are not eternal jewels in the night, but fleeting lights drifting apart. Human existence itself is framed within this expansion, a brief spark between the birth of space-time and its eventual fate. Yet the expansion also carries hope. It explains the origin of structure, the growth of galaxies, the possibility of life. Without it, the universe might have collapsed back upon itself, or remained an undifferentiated fireball. Expansion gave time for stars to form, for elements to build, for consciousness to arise. It is both the destroyer and the giver of worlds. Today, astronomers map the expansion with ever greater precision. Instruments like the Hubble Space Telescope, the Planck satellite, and now the James Webb Space Telescope peer into the past, measuring the redshift of ancient galaxies, the faint glow of the microwave background, the clustering of matter across billions of light years. Each measurement refines the story, yet deepens the mystery. Is the expansion uniform everywhere, or do different regions evolve differently? Is dark energy constant, or does it change over time? Could the acceleration be a hint that Einstein's equations themselves are incomplete, pointing toward a deeper theory of space-time yet to be discovered? The answers remain hidden in the stars, in the voids, in the trembling of ancient light. The expanding universe is more than a scientific fact. It is a story of transformation, of a cosmos that began in fire and now drifts toward silence. It is a reminder that nothing, not galaxies, not stars, not even space-time, endures forever. Yet, it is also a reminder of wonder. For in its expansion, the universe carries the memory of its birth, written in the faintest photons, the most distant galaxies, the trembling of space-time itself. Every moment, as galaxies rush apart, the universe writes a new page in its story. And humanity, for a brief instant, has the privilege of reading it. The phantom force, dark energy. For most of human history, the night sky seemed eternal. Stars wheeled overhead, galaxies shimmered faintly, and the cosmos appeared vast but still. It was only in the 20th century that the illusion of stillness was shattered. The universe was expanding, galaxies rushing away as though pushed by some invisible hand. At first, it was assumed gravity would slow this flight. Like stones thrown upward, galaxies would eventually succumb to their mutual pull. Perhaps they would drift to a stop, or even collapse back into a fiery end. That was the expectation, orderly, familiar, bound to the logic of Newton and Einstein alike. But in 1998, astronomers discovered something astonishing. By studying distant type Ia supernovae, exploding stars that serve as cosmic mile markers, they found the universe was not slowing down. It was speeding up. The farther they looked, the faster galaxies fled. Expansion was accelerating. Something unknown was at work, something no theory had anticipated. A force without substance, a pressure without source. Physicists gave it a haunting name: dark energy. Dark energy is the most powerful phenomenon in the cosmos, yet it is invisible, untouchable, beyond direct detection. It fills the vacuum of space, driving galaxies apart with a steady push. Today, it accounts for nearly 70% of the universe's total energy content. Ordinary matter, stars, planets, human bodies, makes up less than 5%. The cosmos is not what it appears to be. But what is dark energy? That remains one of the deepest mysteries in science. One possibility is that it is the cosmological constant, a term Einstein himself introduced into his equations of general relativity. He had added it reluctantly to keep the universe static, only to abandon it when Hubble revealed expansion. Yet perhaps it was no blunder at all. The cosmological constant may represent the energy of the vacuum itself, a property of spacetime that resists compression and drives expansion. Quantum field theory predicts that even empty space is not truly empty. Virtual particles flicker in and out of existence, borrowing energy from nothing and returning it. This restless sea of quantum fluctuations should contribute to vacuum energy. But the numbers do not align. Theory predicts a value vastly larger, by a factor of 10 to the power of 120, than what is observed. This is the most catastrophic mismatch between theory and experiment in all of physics, a riddle without solution. Other scientists propose that dark energy is not constant but dynamic, a field evolving with time. They call this idea quintessence, after the ancient notion of a fifth element beyond earth, air, fire, and water. Quintessence would change over cosmic history, perhaps growing stronger or weaker, perhaps vanishing altogether. If so, the fate of the universe is not fixed. Dark energy could fade, allowing gravity to slow expansion, or it could intensify, accelerating expansion to catastrophic levels. The most terrifying possibility is phantom energy, a form of dark energy with properties so extreme that it would tear spacetime itself apart. If phantom energy exists, the expansion would accelerate without limit. Galaxies would drift apart. Stars would be pulled from galaxies, planets from stars, and finally, atoms from themselves. Even the very fabric of spacetime would unravel in a final convulsion, the Big Rip. In this vision of the end, the arrow of time would not fade into heat death, but race toward annihilation, as if the universe itself were fleeing from existence. Yet the mystery deepens. Could dark energy be a signal that Einstein's equations are incomplete? Some physicists suggest that what we see as accelerated expansion may not be a new force, but a hint of new physics, extra dimensions, modifications to gravity, or unknown interactions between spacetime and quantum fields. Others wonder whether dark energy could be tied to the fate of the vacuum itself. If the universe exists in a false vacuum, a metastable state, not the lowest possible energy, then one day it could decay to a true vacuum. Such a collapse would rewrite the laws of physics, propagating at the speed of light, erasing all structure in an instant. The accelerating universe might be the faint tremor of this instability. Observations continue to refine the mystery. Telescopes measure the clustering of galaxies, the distortions of light by gravity, the faint ripples of the cosmic microwave background. Projects like the Dark Energy Survey, the Euclid mission, and the Vera Rubin Observatory seek to chart cosmic expansion across billions of years. Each data point tightens the picture, yet the nature of dark energy remains elusive. The results so far suggest that dark energy behaves like the cosmological constant, steady, unchanging, uniform. But the margins are thin, and the unknown looms large. Philosophically, dark energy confronts humanity with a universe stranger than imagination. If 70% of reality is made of something we cannot see or touch, what does it mean to know the cosmos at all? Our instruments, our equations, our very senses perceive only the surface. Beneath it lies an ocean of mystery, a phantom force that determines the fate of everything. For some, this is terrifying. For others, it is awe-inspiring. The accelerating universe suggests not finality, but possibility, that the cosmos holds layers of reality not yet unveiled. Dark energy may be a clue to deeper laws, to unification of relativity and quantum mechanics, to a new understanding of spacetime itself. The fate of the universe rests in the answer. If dark energy is constant, expansion will continue forever, galaxies receding into silence until only darkness remains. If it is quintessence, the story could take unexpected turns, slowing, collapsing, bouncing into new universes. If it is phantom, existence will end in violence, every bond torn apart. In every case, the destiny of the cosmos is written not in stars, but in the invisible hand of dark energy. Perhaps the most haunting thought is this: we live in a privileged era. We can see the cosmic web in its fullness, galaxies strung across spacetime like jewels on filaments. In the far future, accelerated expansion will erase this vision. Distant galaxies will vanish beyond the horizon, their light stretched until it never reaches us. Civilizations to come may believe themselves alone, trapped in a lonely island of stars, the evidence of cosmic history erased. The universe, in its acceleration, is hiding its own origins from its children. Dark energy is the phantom force shaping existence. It is the silence between galaxies, the pressure that stretches reality, the haunting whisper that the cosmos may not be as it seems. It is not merely a scientific puzzle. It is the greatest reminder that what is visible, what is known, what is familiar, is only the surface of a much deeper mystery. And until its nature is revealed, dark energy remains the most haunting secret of spacetime. The singularity problem. In the language of Einstein's equations, gravity is the bending of spacetime. Mass and energy tell the fabric how to curve, and curvature tells matter how to move. For planets and stars, for galaxies and clusters, this description is elegant and precise. But hidden within the mathematics are solutions that seem to defy reason. Places where curvature becomes infinite, where spacetime folds in on itself and the laws of physics collapse. These places are called singularities. At a singularity, equations lose meaning. Distances shrink to nothing. density grows without limit, and time itself may end. To enter such a realm is to abandon the language of science for the silence of paradox. And yet, singularities are not abstract. They are the hearts of black holes. They may even lie at the beginning of the universe itself. The singularity problem is one of the most profound riddles in physics. It is the fault line where relativity and quantum mechanics, the two greatest theories of the 20th century, clash and fail. The story begins with collapse. When a massive star exhausts its nuclear fuel, gravity has no opponent. The core implodes, compressing matter to extremes. If the mass is sufficient, not even neutron degeneracy, the pressure of neutrons packed tightly together, can halt the collapse. The star shrinks beyond its Schwarzschild radius, and a black hole is born. General relativity predicts that inside this event horizon, collapse continues until the core shrinks to a singularity, a point of infinite density where space-time curves infinitely. Nothing escapes, not even light. The horizon is the point of no return, and the singularity the ultimate abyss. But infinities are signs of broken theory. Nature rarely deals in infinities. They are human markers of ignorance, of equations pushed beyond their domain. The singularity signals not reality itself, but the failure of relativity to describe it. Stephen Hawking and Roger Penrose explored these ideas in the 1960s, proving the singularity theorems. Under general conditions, they showed, singularities are unavoidable. If general relativity is correct, then black hole singularities must form. More unsettling still, the universe itself may have begun in one, the singularity of the Big Bang, where space-time itself was born. But this leaves an impossible paradox. How can the cosmos begin in a point of infinite density? How can time itself emerge from a place where time has no meaning? Relativity alone cannot answer. Something deeper must exist. The clash becomes sharper with the information paradox. In the 1970s, Hawking showed that black holes are not eternal prisons. Quantum effects near the horizon allow them to emit radiation, slowly evaporating over time. This Hawking radiation means that black holes can vanish, but if they disappear completely, what happens to the information about everything that fell inside? Quantum mechanics insists that information cannot be destroyed, yet relativity suggests it is lost forever. The contradiction is stark. Either relativity fails, or quantum theory does. Both cannot be true together. This paradox has haunted physics for decades. Entire fields of thought, from string theory to holography, have arisen in pursuit of resolution. Some propose that information is stored on the event horizon, encoded in its surface like a cosmic hologram. Others suggest that space-time itself is emergent, arising from deeper structures where information is fundamental. In this view, the singularity is not a place in space, but a flaw in description. The real answer may lie in a theory of quantum gravity uniting relativity and quantum mechanics into a deeper whole. String theory offers one possibility. It replaces point particles with vibrating strings, whose interactions smooth out the infinities of singularities. In some models, black hole singularities are replaced by tangled webs of strings and branes, where space-time itself dissolves into more fundamental ingredients. Loop quantum gravity offers another path. Here, space-time is discrete, woven from finite loops at the Planck scale. In such a universe, singularities may be avoided entirely. Instead of infinite collapse, the density reaches a maximum, then bounces. Black holes could give way to white holes. The Big Bang may have been a big bounce, the rebirth of a cosmos from a prior collapse. These ideas remain untested, glimpses of possible futures. Yet they point toward a haunting truth. Spacetime, as Einstein described it, may not be fundamental. It may be an approximation, like fluid dynamics describing water without revealing the molecules beneath. Singularities may be the cracks where the deeper structure shows through. The singularity problem also invites radical speculation. Some suggest that black holes might seed new universes, each singularity a portal to another spacetime. In this view, our cosmos could itself have been born from the collapse of a black hole in a parent universe. The laws of physics may be shaped by such cosmic natural selection, universes giving birth to universes through singularities. Others imagine that singularities may not be places of destruction, but of transition, gateways where the rules of one reality give way to another. Wormholes, white holes, baby universes. These are not proven, but they are consistent with the idea that singularities are not ends, but beginnings. Yet the paradox remains unresolved. Observations push ever closer to the horizon. The Event Horizon Telescope has imaged the shadows of supermassive black holes, confirming Einstein's equations to exquisite detail at their boundaries. Gravitational wave detectors reveal the mergers of black holes, their final dances encoded in ripples of spacetime. But the singularity itself remains hidden. It lies behind horizons, cloaked in silence, unreachable by light or signal. It is the forbidden heart of spacetime, a place that may exist yet can never be observed. This raises a philosophical question. If a singularity can never be seen, does it exist in any physical sense? Is it a real feature of the cosmos, or merely a failure of mathematics? Perhaps both. Perhaps reality itself hides its deepest truths behind veils of inaccessibility. What is clear is that singularities are warnings. They mark the boundaries of knowledge, the edges of maps where equations fail. To confront them is to confront the limits of science. And yet, they are also invitations. For if singularities are resolved, if a deeper theory of spacetime emerges, it will be nothing less than the unification of physics, the reconciliation of gravity and quantum mechanics, the unveiling of the true architecture of reality. Philosophically, the singularity problem forces a rethinking of existence itself. If the Big Bang was a singularity, then the entire cosmos was born from a place beyond time. If black holes end in singularities, then countless regions of spacetime collapse into places where the story of physics stops. These are not merely curiosities. They are the most extreme expressions of the haunting secrets of spacetime. Perhaps, in the end, the singularity is not a place, but a question. The question of what lies beyond physics as we know it. Until that answer comes, singularities remain the darkest mirrors of the cosmos, reflecting back not the universe's failures, but our own. Wormholes and white holes. The fabric of spacetime is not passive. It bends, it ripples, it collapses into black holes and stretches with cosmic expansion. But hidden within Einstein's equations are solutions that are stranger still. Structures that suggest shortcuts through the cosmos, or even pathways into other realms. They are called wormholes, and their mirror opposites, white holes. To imagine them is to step beyond the familiar, into the speculative frontier where mathematics whispers possibilities that reality may or may not allow. Wormholes and white holes are not yet observed. They remain dreams within the equations. But they are among the most haunting dreams physics has ever conjured. The story begins with Einstein himself. In 1935, together with Nathan Rosen, He studied the mathematics of general relativity and discovered a curious solution. Black holes, instead of being bottomless pits, could connect to mirror regions of spacetime. The result was what came to be called an Einstein-Rosen bridge, a tunnel through spacetime, linking two distant points. In theory, such a bridge could connect not only places, but times, enter one mouth and emerge elsewhere, or elsewhen. To a civilization that could control such pathways, the universe would shrink, distances collapsing into traversable corridors. But the mathematics was cruel. Einstein-Rosen bridges, as originally conceived, are unstable. They collapse too quickly for anything to cross. Like dreams, they vanish the moment one tries to grasp them. Decades later, physicists revisited the idea. Could exotic matter, matter with negative energy density, hold wormholes open? Quantum theory allows for such energy in small amounts, glimpsed in phenomena like the Casimir effect, where vacuum fluctuations create measurable forces. If enough exotic matter could be harnessed, a wormhole might remain stable, wide enough for passage. This possibility has fueled imagination. Wormholes populate science fiction, from interstellar travel to time machines. Yet in physics, they remain uncertain. Negative energy is real, but whether it exists in the required quantities is unknown. And even if wormholes could exist, keeping them stable against collapse may be impossible. Still, the idea lingers, like a mirage in the mathematics of spacetime. Opposite to black holes and wormholes lies another theoretical entity, the white hole. If a black hole is a region from which nothing can escape, a white hole is its time reverse, a region into which nothing can enter. Instead of devouring matter, it expels it. Instead of drawing in light, it erupts with it. White holes emerge naturally from the equations of relativity, paired with black holes as mirror solutions. Yet unlike black holes, no white hole has ever been observed. They remain purely hypothetical, ghostly shadows of the mathematics. And yet, speculation persists. Could the Big Bang itself have been a kind of white hole, an eruption of spacetime from nothing? A one-time expulsion of matter and energy that became the cosmos? Some physicists explore this possibility, imagining the universe not as born from a singularity, but from a white hole event. Wormholes and white holes are haunting not only for what they suggest, but for what they reveal about spacetime itself. They remind us that Einstein's equations are not just descriptions of familiar gravity, but windows into landscapes of possibility. They hint that spacetime may allow topologies far stranger than flat planes or gentle curves, tunnels, passages, and fountains of matter and light. If wormholes exist, they could connect regions of the same universe, or even bridge universes in a multiverse. They could allow travel faster than light, not by breaking relativity, but by bending spacetime itself. They could permit loops in time, raising the specter of paradox. The grandfather paradox, causal loops, self-consistent histories, all emerge in the mathematics of traversable wormholes. In this sense, wormholes are not just tools of imagination. They are tests of the boundaries of physics, forcing us to confront questions of causality, determinism, and the nature of reality. The search for evidence continues. Astronomers watch for signatures in the cosmos, strange lensing of light, anomalous bursts of radiation, unexplained flares near black holes. Could some of these phenomena be hints of wormholes, masquerading as ordinary objects? No definitive evidence has emerged, but the possibility cannot be dismissed. Meanwhile, quantum gravity, whether through string theory, loop quantum gravity, or holography, explores whether wormholes might exist at the deepest levels of spacetime. Some recent work suggests a profound connection. Wormholes may be linked to entanglement, the mysterious quantum correlation between particles. In a bold conjecture, Juan Maldacena and Leonard Susskind proposed ER equals EPR, the idea that Einstein-Rosen bridges, ER, are the same as entangled pairs, EPR. If true, then every quantum entanglement may be a tiny wormhole, a thread of spacetime connecting distant regions of reality. In this vision, the cosmos itself is woven from wormholes, and spacetime emerges from the network of entanglement. Wormholes are not anomalies, but the very threads of the fabric. White holes, too, invite speculation. Some propose that black holes may not end in singularities, but rebound into white holes, spewing their contents into new regions of spacetime. Such a bounce could resolve the information paradox, ensuring that nothing is truly lost. Others suggest that microscopic white holes might exist, relics of the early universe, tiny fountains of matter awaiting discovery. If any of this is true, the cosmos is stranger than anyone imagined. Philosophically, wormholes and white holes embody the tension between possibility and impossibility. They are permitted by mathematics, but resisted by physical intuition. They challenge the boundaries between science and imagination, between equations and existence. To contemplate them is to confront the haunting flexibility of spacetime. It is not rigid, not fixed, but a canvas capable of painting tunnels, bridges, and eruptions. It suggests that reality is not confined to what is seen, but is shaped by hidden geometries beyond perception. Whether wormholes and white holes exist in the physical universe may remain unknown for centuries. But even as abstractions, they reveal that spacetime is not merely a stage. It is an actor with possibilities as strange as dreams. If wormholes could be traversed, they would change everything. Distance would vanish. The universe would open like a labyrinth with secret doors. Time itself might be navigated, the arrow bent or broken. Humanity would no longer be bound to one planet, one galaxy, one moment. If white holes exist, they could explain the deepest mysteries: the origin of the universe, the fate of information, the rebirth of collapsed stars. They could transform endings into beginnings, singularities into fountains. And if neither exist, they still reveal something profound: that spacetime is not simple. It holds within it the capacity for structures beyond ordinary imagination, even if reality never chooses to manifest them. The haunting beauty of wormholes and white holes is not only in their promise, but in their reminder. They remind us that the universe is not obliged to conform to expectation. It may harbor corridors and fountains, tunnels and eruptions, or none at all. It may be shaped by geometries so alien that even imagination strains to contain them. And until the truth is known, wormholes and white holes remain as they began, shadows in the equations, whispers in the mathematics, haunting possibilities in the fabric of spacetime. Time paradoxes. Time, as lived, feels simple. It flows forward, carrying lives from past to present, from present to future. Yet in the mathematics of relativity, time is not a river, but a dimension, bound to space, pliable, curved. And within those equations lies a haunting possibility: loops in time. Paths through spacetime that bend so deeply they reconnect with themselves. In such worlds, the future could reach back into the past. Cause and effect could twist into knots. These are closed time-like curves, solutions to Einstein's field equations that permit time travel. They are not inventions of fiction. They arise naturally from the mathematics of spacetime, and they open the door to paradox. One of the simplest examples is the Gödel universe. In 1949, mathematician Kurt Gödel discovered a rotating cosmological solution to relativity. In his universe, the rotation of matter allowed for paths that looped back in time. An observer could travel into their own past, not by breaking physics, but by following spacetime's geometry. Other solutions, too, allow for such curves. Wormholes, if traversable, could connect different times as well as places. The immense frame-dragging near-rotating black holes, the twisting of spacetime by their spin, could, in theory, permit loops in time. The mathematics is clear. Relativity allows time travel. The problem is not possibility, but paradox. The most famous is the grandfather paradox. Suppose someone travels back in time and prevents their grandfather from meeting their grandmother. They would never be born, and thus could not travel back to alter the past. Cause destroys effect. Effect destroys cause. Another is the bootstrap paradox. Imagine a scientist who receives instructions from her future self, builds a machine, and then travels back to give those same instructions to her younger self. Where did the information originate? It exists in a loop, without cause, without beginning. These paradoxes reveal the fragility of causality, the logic upon which science itself rests. If past and future can intertwine, does meaning dissolve? Physicists have proposed answers. One is the Novikov self-consistency principle. It argues that events on closed time-like curves must be consistent. Paradoxes cannot occur. A traveler may go back in time, but whatever they do will already be part of history. Attempting to change the past will only fulfill it. The universe protects itself, ensuring consistency. In this view, free will bends under physics. Choices that seem open, constrained by necessity. Time travel becomes possible, but paradox forbidden. The loop is self-contained, immutable. Others argue differently. They suggest that time travel would fracture reality into branches, parallel timelines in which each choice is realized. In this many worlds interpretation, traveling back does not change the past, but creates a new history, leaving the original intact. Paradoxes vanish, replaced by a multiverse of diverging realities. Both views raise unsettling questions. Is reality self-consistent and closed, or endlessly branching and infinite? Is free will real, or an illusion bound by geometry? Quantum mechanics deepens the riddle. At the quantum scale, particles can tunnel through barriers, exist in superpositions, and remain entangled across distances. Some experiments suggest that quantum systems placed on closed time-like curves behave in paradox-free ways, automatically resolving inconsistencies. Information loops can exist without contradiction, though in forms alien to human intuition. This hints that paradox may not be a violation, but a misunderstanding. That at deeper levels, the rules of logic itself are shaped by physics, not the other way around. Philosophically, time paradoxes cut to the core of existence. Human identity is built on cause and effect, childhood shaping adulthood, memories shaping choices. If causality can bend, what becomes of identity? If the future can influence the past, what becomes of responsibility, of choice, of meaning? And yet, paradoxes also reveal the haunting beauty of spacetime. They show that time is not a simple arrow, but a labyrinth. Within its corridors, past and future may mirror each other, entangle, or fold into loops. Existence itself may be stranger than the stories consciousness weaves to contain it. But do paradoxes exist in reality, or only in equations? Observations provide no evidence of time travelers. The cosmos appears consistent, without contradiction. Perhaps physics contains safeguards. Hawking proposed the chronology protection conjecture. The laws of physics prevent closed time-like curves, ensuring paradox never arises. Quantum effects, he suggested, would destabilize wormholes or rotating spacetimes before loops could form. The universe, in this view, conspires to preserve causality. Yet even if time travel is impossible, the paradoxes remain instructive. They force physics to confront its boundaries, to ask why causality feels sacred when equations suggest otherwise. They illuminate the fragility of human understanding, the way certainty unravels when space-time itself bends. Speculation continues. Could paradoxes be avoided not by prevention, but by reinterpretation? Some suggest that time is not fundamental, but emergent. If time arises from entanglement or quantum correlations, then paradox may dissolve in a timeless substrate. Loops and contradictions exist only in the emergent picture, not in the deeper reality beneath. Others imagine that paradox is a signpost, a warning that our theories are incomplete, pointing toward the need for quantum gravity, for a unification that will reveal time not as dimension, but as shadow. For now, paradoxes remain hypothetical. No wormholes are known, no closed time-like curves confirmed. Yet in their very impossibility, they haunt the imagination. They are the echoes of a universe that does not conform to expectation, that permits strangeness even if it forbids its realization. In the silence of thought experiments, in the mathematics of spacetime, time paradoxes whisper of a cosmos where causality bends, where beginnings and endings dissolve, where existence itself is entangled with impossibility. Whether real or not, they remind humanity that time is not the steady current it seems. It is a fabric, woven with possibility, haunted by contradictions, alive with mystery. And perhaps, in those contradictions, lies the key to the deepest secret of all. That time, as lived and remembered, is not the truth of reality, but the fragile story consciousness tells to survive within it. Quantum foam. At human scales, space-time feels smooth. Planets orbit with precision, light travels in straight lines, and the geometry of the universe unfolds like a vast, continuous fabric. Even Einstein's equations treat space-time as a seamless continuum, bending and curving under the weight of mass and energy. But beneath this apparent smoothness lies a frontier stranger than any mountain range or ocean depth. At the smallest conceivable scales, the Planck scale, 10 to the negative 35th meters, space-time itself begins to shudder, dissolve, and erupt in restless chaos. Here, the calm fabric becomes a storm. This is the realm of quantum foam. The idea emerged in the mid-20th century when physicist John Wheeler asked what space-time might look like if quantum mechanics and general relativity were both taken seriously. At macroscopic levels, relativity reigns, describing space-time as smooth and continuous. At microscopic levels, quantum mechanics rules, where uncertainty and fluctuations dominate. Combine them, Wheeler argued, and space-time at the Planck scale could not remain smooth. It would bubble, writhe, and churn like the surface of a stormy sea. Distances and durations would fluctuate violently, twisted by quantum uncertainty. Virtual black holes might pop into existence, then evaporate in flashes of energy. Tiny wormholes could open and close in an instant, connecting regions of space-time before collapsing. The geometry of reality itself would froth and dissolve, a seething foam from which the smooth universe emerges at larger scales. This vision, wild, chaotic, and unobservable directly, remains one of the most haunting ideas in modern physics. Quantum foam is not speculation without grounding. Quantum field theory shows that even empty space is alive with fluctuations. Virtual particles flicker in and out of existence, borrowing energy briefly before vanishing. Space is never truly empty. It is restless, charged with possibility. At the Planck scale, these fluctuations become so intense they reshape space-time itself. The uncertainty principle ensures that the smaller the scale, the greater the energy fluctuations. At 10 to the negative 35th meters, the energy density becomes extreme, enough to bend space-time violently. The result is a foam of constant creation and annihilation, geometry itself unraveling and reforming. It is a realm beyond measurement. To probe it would require energies far beyond any accelerator humanity can build. The Planck energy is 10 to the 19th giga-electron volts, a scale utterly beyond reach. Even the most powerful cosmic rays fall short. Quantum foam is hidden not by distance, but by impossibility. Yet its consequences ripple outward. If space-time is foamy at its foundation, then everything built upon it, particles, forces, galaxies, consciousness, is woven from this froth. The smoothness we see is an illusion of scale, like calm seas that hide the turbulence of molecules. The universe may be structured upon a chaos we can never touch directly. Some theories suggest that quantum foam could explain the cosmological constant, the energy of the vacuum that drives cosmic acceleration. Others propose that it shapes the unification of gravity with quantum mechanics, the long-sought theory of quantum gravity. In string theory, space-time may not be fundamental at all, but emergent from the vibrations of strings and branes. In loop quantum gravity, space-time is granular, composed of finite loops of geometry. In both visions, the foam is not anomaly, but foundation, the true architecture of existence, revealed only at scales too small to see. The foam also raises haunting questions about time. If space-time itself is unstable at the Planck scale, what becomes of the arrow of time? Is it born from the froth, an emergent property of fluctuations? Could time itself dissolve if one looked closely enough? Some physicists speculate that time may not exist at the fundamental level. Instead, it may arise from entanglement, from correlations between quantum states. The foam, in this view, is timeless. What we call the flow of time is an illusion built atop a deeper, chaotic substratum. Attempts to detect signatures of quantum foam continue. Astronomers search for blurring in the light of distant quasars, distortions caused by fluctuations in space-time along their billion-year journeys. Gamma-ray bursts traveling across the cosmos at immense energies may reveal subtle delays if space-time is granular. So far, observations set limits, but no clear evidence. The foam remains hidden, its whispers faint. And yet, indirect clues persist. The holographic principle, born from black hole physics, suggests that space-time's degrees of freedom may scale with surface area, not volume. This hints that the smooth continuum is not fundamental, but emergent from deeper, discrete bits of information. If true, quantum foam is not anomaly, but necessity, the bubbling sea from which holographic reality arises. Philosophically, the foam is unsettling. Humanity imagines space-time as a backdrop, firm and enduring. To learn that it may dissolve at its foundation is to confront fragility. Reality is not solid, but frothing. The stability of stars, of orbits, of life, rests upon chaos so deep it cannot be seen. And yet, there is wonder in this vision. The foam is not destruction, but creation. From its ceaseless fluctuations arises the smoothness of space-time, the stability of atoms, the structure of galaxies. It is the engine of becoming, the foundation of all that exists. Some go further. They ask whether quantum foam might be the birthplace of universes themselves. If space-time fluctuates violently at small scales, perhaps entire regions can inflate, budding off new universes in endless succession. Our cosmos may be one bubble in an infinite froth, a child of the foam. If so, then the deepest secret of space-time is that it is not singular. Reality is not one fabric, but many, each born from fluctuations beyond comprehension. The multiverse itself may be woven from quantum foam. In the end, quantum foam is more than theory. It is a reminder of limits. It tells us that beneath every law, every certainty, lies uncertainty. Beneath the smoothness of space-time lies turbulence. Beneath the vast calm of the cosmos lies chaos unending. It is both humbling and haunting. For if space-time is foamy, then the universe we know is built on a storm we will never touch, a chaos forever hidden, yet always present. And perhaps that is its greatest secret, that reality, in its deepest foundations, is not still but restless, not smooth but seething, not certain but forever uncertain. Quantum foam is the ghost beneath the fabric, the turbulence beneath the calm, the haunting heartbeat of space-time itself. Multiverse horizons. On clear nights, the universe feels boundless. Galaxies glitter across the sky, stretching outward as far as telescopes can see. Yet however vast it appears, the observable universe is finite, limited by the speed of light and the age of the cosmos. Beyond that horizon, 46 billion light-years away in every direction, lies a veil of invisibility. But what lies beyond that veil? For decades, cosmologists have wrestled with this question, and the answers, drawn from theory and mathematics, point towards something staggering: that our universe may not be the only one, that what we see, the galaxies, the stars, the cosmic web, may be one bubble in an endless sea of bubbles, each with its own laws of physics. This is the haunting idea of the multiverse. The seeds of this vision were planted in the theory of cosmic inflation. In the early universe, space-time expanded exponentially, stretching quantum fluctuations into the seeds of galaxies. But inflation, once begun, may not end everywhere at once. Instead, it continues, eternally in some regions, while stopping in others. The result is a froth of expanding bubbles, each one a universe. Ours is one among them. This scenario is called eternal inflation, and it suggests that the multiverse is not speculation, but consequence, the natural outcome of inflationary physics. Each bubble may contain different constants, different particles, even different dimensions. The laws of physics themselves may be local, varying from universe to universe. But inflation is not the only road to the multiverse. Quantum mechanics, too, offers its own branching vision. In the many worlds interpretation, every quantum choice, every particle's spin, every photon's path, creates new branches of reality. In this picture, universes proliferate endlessly, splitting at every moment. In one, a star collapses into a black hole. In another, it survives. In one, a decision is made. In another, its opposite. All outcomes exist, woven into an infinite branching tree. These visions are speculative, but grounded in mathematics. They suggest that our universe, far from unique, is part of an ensemble beyond imagining. The implications are haunting. If countless universes exist, then the fine-tuning of our cosmos, the delicate balance of forces that allow stars, planets, and life, may not be a miracle, but a selection effect. In most universes, conditions are sterile. In a few, like ours, they allow complexity. Life arises not because the universe is designed, but because in an infinite multiverse, some universes must allow it. This anthropic principle is unsettling. It shifts the question from why this universe to why not this one. It suggests that meaning may be statistical, not absolute. But the multiverse also raises paradoxes. If other universes exist, can they ever be observed? The cosmic horizon forbids it. Light from beyond can never reach us. Even gravitational waves, even neutrinos, are bound by the same limits. Other universes may exist forever beyond reach, real but inaccessible. And yet, some physicists search for clues. Collisions between universes in the inflationary picture could leave imprints in the cosmic microwave background. Circular scars, faint anomalies in the afterglow of the Big Bang. Others propose that entanglement across horizons might reveal hidden correlations. No evidence has yet been found, but the search continues. Speculation grows bolder still. String theory suggests a landscape of possible universes, each with its own vacuum state, its own geometry, its own physics. The number of possibilities is staggering, 10 to the power of 500 or more. If string theory is correct, then the multiverse is not optional but inevitable, a vast array of realities scattered across the cosmic landscape. Others imagine that black holes themselves may spawn new universes. In this picture, the singularity is not an end, but a beginning, a seed that blossoms into another cosmos. Our universe may be a child of another and may in turn give birth to others through its own black holes. Reality becomes a tree of universes, branching eternally. Philosophically, the multiverse confronts humanity with vertigo. It dissolves uniqueness, replacing it with infinity. It suggests that everything possible happens somewhere. Every life lived, every choice made, every story told. In such a cosmos, meaning becomes fragile. What is one life against infinity? What is one universe against countless? And yet, there is also wonder. For the multiverse, if real, expands imagination beyond limit. It tells us that reality is not one stage, but countless stages, each with its own play. It suggests that the cosmos is not bound by necessity, but alive with possibility. Still, the multiverse remains unproven. Critics argue that it is metaphysics, not physics, if it cannot be tested. Others reply that it may leave indirect fingerprints, that theory and observation together may reveal its presence. The debate continues, fierce and unresolved. But whether real or not, the idea of the multiverse reshapes human thought. It forces a reconsideration of existence, of meaning, of reality itself. It asks whether spacetime, as vast as it seems, is only a fragment of a greater whole. The horizon remains vast and silent. Beyond it may lie emptiness or infinity. Beyond it may lie nothing or everything. And until the veil is lifted, the multiverse remains a haunting possibility, a secret of spacetime that whispers from beyond the edge of sight. The future of spacetime. The night sky feels eternal. Stars glitter, galaxies drift. Space-time itself stretches across the infinite darkness. Yet the universe is not timeless. It is changing, restless, and its future is written into the very fabric of space-time. To ask about the destiny of space-time is to ask about the fate of everything. Galaxies, stars, atoms, even the laws that bind them. The expanding tapestry. Ever since Edwin Hubble revealed that galaxies are rushing away, humanity has known that space-time itself is stretching. But the 1998 discovery of accelerated expansion transformed this knowledge into something far more haunting. Dark energy, a mysterious force woven into the vacuum, pushes galaxies apart faster and faster. If this acceleration continues, the distant cosmos will vanish. Galaxies beyond the local group will slip over the horizon, their light stretched until it never reaches us. In tens of billions of years, the night sky will fade to darkness, stripped of its grandeur. To observers in that distant future, the universe will appear small, isolated, and silent. The evidence of cosmic origins will be erased by space-time itself. The heat death. The most widely accepted future is called the heat death of the universe. As expansion continues, galaxies burn through their fuel. Stars age and die. White dwarfs cool into black embers. Neutron stars fade. Black holes evaporate in Hawking radiation. Matter itself may decay into radiation. In this future, space-time stretches endlessly, thinning all energy into uniformity. Entropy approaches its maximum. No differences remain. No gradients to power processes. No heat to flow. No time to measure. The arrow of time, born from entropy, dissolves into silence. It is a future not of fire, but of stillness, the ultimate fading of existence. The Big Rip. Yet another possibility is more violent. If dark energy grows stronger over time, its acceleration could become catastrophic. Galaxies would be torn from one another, then stars from galaxies, then planets from stars. Eventually, even atoms would be ripped apart, space-time itself shredded. This is the Big Rip, an apocalypse where the fabric of the cosmos unravels. Unlike heat death, which arrives slowly, the Big Rip ends everything in a final convulsion. It is the most terrifying destiny, space-time itself destroyed by the very force that drives it. The Big Crunch. Some theories allow for the opposite. If dark energy weakens or reverses, gravity could halt expansion. Galaxies would slow, then drift back together. Stars and clusters would collide. The cosmos would collapse inward, heating as it shrinks. Eventually, everything would converge into a final singularity, the Big Crunch. This fate mirrors the Big Bang in reverse. Space-time would not stretch, but fold back upon itself. Time might end or begin again in a new cycle. Some physicists imagine an eternal Big Bounce, where universes expand and collapse endlessly, each cycle birthing a new arrow of time. Quantum horizons. At the smallest scales, quantum theory reshapes the future. Loop quantum gravity suggests that singularities may bounce instead of collapse, hinting at rebirth. String theory offers extra dimensions, hidden geometries that could guide destiny. The holographic principle whispers that space-time may not be fundamental at all, but emergent, a surface woven from deeper laws of information. If so, the future of space-time is not only a question of expansion or collapse, but of transformation. The universe may evolve into a reality where space-time itself is no longer the stage, but an illusion replaced by something deeper, the human horizon. For humanity, the question is not only what fate awaits space-time, but whether we will be there to witness it. Stars like our sun will burn for billions more years, but civilizations are fragile. If intelligence endures, it may spread across galaxies, harnessing stars, building Dyson spheres, navigating the currents of expansion. Perhaps distant descendants will ride wormholes, bending space-time itself. Perhaps they will seek escape into other universes, should such paths exist. Or perhaps they too will vanish, their achievements erased by time. In either case, the future of space-time is the future of meaning, of whether existence itself has continuity. Philosophical horizons. The fate of spacetime is not merely scientific. It is philosophical, even existential. If heat death comes, then all stories end in silence. If the Big Rip arrives, then existence ends in violence. If cycles repeat, then eternity may be an endless loop. Each possibility carries weight. Does existence have purpose if it ends? Does meaning vanish with entropy? Or does the beauty of the cosmos lie not in permanence, but in the fleeting spark of order within chaos? Spacetime, in its future, confronts humanity with humility. It reminds us that permanence is illusion. It reminds us that the universe is fragile, restless, impermanent. And yet, it also reveals wonder. For even in its most haunting futures, spacetime allows life, thought, and reflection. It allows the universe to know itself, if only briefly, the unknown. Despite the models, the future of spacetime is not certain. Dark energy may change. New physics may emerge. Singularities may conceal rebirths. What seems final may only be transition. Perhaps the greatest truth is that the future of spacetime is still unwritten. Humanity looks into the night sky and sees not certainty, but mystery. The answers lie beyond horizons not yet reached. Spacetime was born in fire, and it will end in silence, or collapse, or transformation. Whatever its fate, it carries within it the haunting reminder that all things, galaxies, atoms, lives, are fleeting patterns in a restless fabric. And perhaps that is meaning enough. To know that for a brief span, in one corner of spacetime, the universe looked inward and wondered about its own future. The final reflection, spacetime's secret. Spacetime is the silent stage upon which existence unfolds. Every galaxy, every star, every life has played its part upon this invisible fabric. Yet after a century of discovery, after revolutions in relativity, quantum theory, and cosmology, the true nature of spacetime remains shrouded in mystery. It bends and curves, guiding planets and light. It ripples when stars collide. It collapses into black holes and stretches into cosmic voids. It may foam at the Planck scale, fragment into bubbles of multiverses, or dissolve into illusions born of deeper laws. And through it all, humanity has searched for meaning, for the secret hidden in its silence. But perhaps the most haunting truth is that spacetime resists final answers. Each revelation opens another door. Each certainty dissolves into deeper uncertainty. The fabric of reality itself seems woven not from clarity, but from questions, the illusion of fundamentals. Einstein gave the world a new vision, spacetime as a continuum, alive and dynamic. But quantum theory undermined that vision, suggesting that beneath smoothness lies chaos. Black holes tear the fabric, singularities break the equations, dark energy stretches it into silence. Physicists now ask whether spacetime is even fundamental. Could it be emergent, a property arising from information, from entanglement, from patterns more basic than geometry? The holographic principle suggests that reality is encoded on surfaces, not volumes. ER equals EPR suggests that wormholes and entanglement are one and the same, that spacetime itself is woven from correlations. If true, then spacetime is not the stage but the story, a narrative told by deeper structures, a mirage born from mathematics we have only begun to glimpse. The human struggle with mystery. To live within spacetime is to live within limits. Human lives are measured by time, shaped by entropy, bound to an arrow that flows only forward. Stars may last billions of years, galaxies trillions, but even they will fade. Against cosmic time, human existence is a brief spark. Yet within that spark lies something extraordinary: awareness. Consciousness allows the universe to reflect upon itself, to look into the fabric of space-time and ask what it means. That act of questioning is itself part of space-time's story. Matter shaped into mind, mind shaped into wonder. It is haunting to realize that every thought, every memory, every moment of love or grief is written into space-time, stitched into its geometry, never to be undone. Time may flow, but the fabric records all paths. Existence is fleeting, but space-time holds it forever, the limits of knowing. Science has illuminated much: the bending of light, the ripples of gravitational waves, the structure of the cosmic web. Yet the most profound questions remain unanswered. What is the true nature of dark energy? What lies inside a singularity? Is space-time fundamental or emergent? Does the multiverse exist beyond the horizon? Is time an illusion? Each answer pursued reveals more mystery. The closer physics approaches the heart of space-time, the more it dissolves into paradox. Perhaps this is inevitable. Perhaps reality is not fully knowable from within, just as the eye cannot see itself. But even within uncertainty, there is meaning. For the act of seeking itself reveals something about the universe, that it can give rise to beings capable of wonder, of humility, of awe. The mirror of existence. Space-time is more than physics. It is a mirror. It reflects the impermanence of life, the inevitability of change, the fragility of order. It teaches that all things, stars, civilizations, selves, are temporary. But it also teaches that within impermanence lies beauty. Without entropy, no arrow of time would flow. Without expansion, no galaxies would form. Without fragility, no life would emerge. The haunting secret of space-time is not only its mystery, but its generosity. From its fabric, matter clumped into stars. Stars forged elements. Elements built life. From the silence of equations arose minds capable of asking why. We are not separate from space-time. We are woven into it, threads in its fabric, fleeting expressions of its restlessness. The final reflection. Perhaps the greatest secret of space-time is that it has no single secret. It is not one mystery, but many, layered and infinite. Each generation uncovers one veil, only to find another. Each theory explains much, yet leaves more unexplained. The universe may never reveal its ultimate truth, but in that unknowing lies a deeper meaning: the journey itself, the act of asking, the endless pursuit. For to seek the secret of space-time is to participate in it. To wonder is to be part of its unfolding. To live is to embody its arrow. And so, as the stars drift apart and the cosmos evolves towards silence, one truth remains. For a fleeting moment, space-time looked inward. It gave rise to life, to thought, to beings who asked what space-time itself might be. That question, unanswered, perhaps unanswerable, is itself the final reflection. Space-time is not only the fabric of existence, it is the mystery that makes existence meaningful.